So we're delighted to have Greg Valiant here from Stanford. Oh, sorry. Yeah, delighted to have Greg here from Stanford. Greg, let us know how you want to do questions, if you want to do the chat, or if people should unmute, and take it away.
Yeah, well, thanks so much for having me. And yes, please, the more questions, the better. And yeah, feel free to just unmute yourself and ask, or you could also ask them in the chat, and I'll try to watch the chat. But if I miss a question, please unmute and just interrupt and ask your question. Okay, cool. So I'm going to talk about, I guess, two different settings in sequential prediction. And this is all joint work with Mingde Chao, who's one of my PhD students. And this photo is pretty apt. It looks like he has a halo, and he actually he's phenomenal. Okay, so and I guess this kind of falls into this broader space of problems I've been thinking about, which is sort of how do you think about learning and estimation, where you know, in settings where maybe you try to remove most or all of the usual assumptions on the underlying data.
Yeah, if you want, we can meet tomorrow or. Yeah.
Oh, okay, good. So in the first part, I'll talk about calibration. So we'll be in this sequential binary prediction setting, maybe the sort of one of the most clean and simple settings that you could think about. So we'll have the sequential game between us, the forecaster, and nature / an adversary. So at each time step, and there will be capital T time steps, the adversary, nature, is going to have some outcome, 0 or 1. And think of this as being, you know, is it going to rain today or not? And simultaneously, the forecaster, us, is going to output some probability, which, you know, should correspond to kind of a prediction about the probability that it's going to rain today. Okay, and crucially, both the you know, nature's choice of whether it rains or not, as well as our prediction, will depend arbitrarily on, you know, all of the history up until, you know, up through yesterday. Good. So, so in this sequential prediction game, it's a nature, everyday nature picks a binary outcome. We output a probability. The usual prediction loss represents, you know, how similar are our predictions and the outcomes. Okay, so the, you know, L1 prediction loss would just be the sum over the capital T time steps of the difference between the outcome and the prediction loss. Calibration represents a sort of orthogonal notion of success. So calibration is going to try to characterize to what extent do our predictions actually correspond to probabilities. Okay, so when we say, I think it's going to rain today with probability, you know, I think there's a 60% chance today of rain. To what extent does this 60% actually correspond to a probability? So formally, this calibration error is going to be the following. So it's going to be a summation over the set of probabilities that we predict. And for each probability P that we've predicted, there'll be a term contributing to our calibration error. And this term is going to be the difference in these two quantities. One of them is, or this quantity here on the right is P times the number of days when we predicted P. And we're looking at the difference between this and actually the number of times the outcome was of 1 on days when we predicted P. Okay, so maybe stare at this for a second. On the next slide, we'll kind of maybe reinforce this a little bit. Okay, so pop quiz. So suppose the true sequence of outcomes is just random coin flips on the top here. And suppose our predictions are, you know, every day we just predict 0.5. Okay, so our prediction loss will be exactly capital T over 2. What do we expect the calibration loss to be? So everybody just get a guess in their mind? Okay, does anyone want to either write in the chat or just blurt out what they think
some like 1 over root n kind of thing.
Yeah, so here I guess we're not scaling by n. If you want, you can, sorry, we're not scaling by capital T, but yeah, so it'll be square root T. And again, we've only predicted one distinct value of P. We've predicted 0.5. And the calibration error would be 0 if on exactly half of these days we got a 1, and on half of the days we got a 0. Because the bits are random and expectation, yeah, we expect half of the bits to be 1, but the standard deviation will be root T, and so the expected calibration error will be on the order of root T. So again, just going back to the definition, right? Of the days when we predict a value P, if this value P actually corresponds to a probability, we would expect P times that number of days when we predicted P, we'd expect this number of outcomes to be a 1. And we're just looking at the difference between that and the actual number of 1s on those days when we predicted P. We're summing this over all of our different, over the set of predicted probabilities P. Okay, so this is known as the L1 calibration error. Is everyone okay with this? Okay, so I guess this notion of calibration dates back at least to to this sort of article in 1950, which was referring to kind of weather forecasts. And again, this is something we all grapple with. When the weather forecast says 30% chance of rain today, what does that mean? And from the view of calibration, if the weather forecaster is calibrated, we hope that it means historically, of the times when the forecaster said 30% chance of rain, we hope that it's rained roughly 30% of the time. If that's not the case, then what does 30% even mean? So again, so if the calibration error is small, that means that you're sort of means that you can regard these predictions as probabilities. If the calibration error is large, then in some sense it means that these kind of probabilities, these predicted probabilities, are sort of meaningless or don't correspond to probabilities. And calibration has sort of become increasingly well, I'd never heard of calibration when I was in grad school, and I feel like most grad students now maybe might have heard of it. So it's had a bit of a renaissance. There's been work both in this online prediction setting, as well as a lot of work in the machine learning community, at least in part because deep neural nets tend to produce very uncalibrated predictions. And then also in the more kind of theory community, calibration has cropped up a lot in the algorithmic fairness community. I guess just for the simple reason that if for some like special demographic, when I predict that they will repay their loans with probably 0.3, if this isn't calibrated, if this 0.3 isn't close to the probability, isn't close to the historical fraction of times they've repaid their loans, this kind of exactly corresponds to one's intuition for what discrimination means, right? So good. So calibration has had somewhat of a renaissance. In the simple binary sequential setting, we still don't understand what how to make the best calibrated predictor. So in this sequential length capital T setting, a paper of Foster and Vora in 98 gave a very simple randomized forecaster that achieves the calibration error of the overall sequence length, capital T to the 2/3. And there is the kind of trivial lower bound that we saw in the pop quiz, corresponding to just, the outcomes are random coin flips. That gives you a square root T calibration lower bound. And, before our work, the gap between these was, completely untouched. And, even after our results, there's still this very significant gap between the a very simple randomized predictor and even the new best lower bounds. So I'll tell you a little bit about some of the ideas that go into our lower bound, even though the actual improvement in the exponent isn't remarkable by any sense. And I think this is actually one of the cleanest binary prediction problems that's still super open. So I really encourage you guys to think about it if you're at all tempted. Good. Sorry, so my little chat tab has disappeared. So if there are any questions, please just please just unmute yourself and ask. Good. So why is it hard to kind of close this gap? Well, the main conceptual obstacle is this notion of cover-ups. So a forecaster can try to act strategically to cover up previous mistakes. In other words, even if the forecaster really thinks that maybe the true probability that it'll rain tomorrow is 0.3, the forecaster might predict something other than 0.3 to try to hide previous mistakes. And trying to figure out how powerful are cover-ups is kind of the main obstacle. So let me illustrate what a cover-up is a bit more concretely. So suppose as a forecaster, you sort of suspect that the sequence will be, maybe the first half of the sequence will be random bits, and then the second half of the sequence will basically be all ones. So a sort of truthful forecaster, would predict 0.5, for the random bit portion, and then predict ones for the remaining ones, and would get a calibration error of something like square root n just from the variance on the random flips. In contrast, a sort of strategic forecaster could predict something like 0.6 for the red things. And after these random bits have happened, there would be quite a big calibration error. However, if the forecaster kept predicting 0.6 for all of these ones, up until the calibration error would keep decreasing, and then the forecaster could just start predicting ones once the calibration error hits 0. So this sort of strategic forecaster is sort of leveraging some sense of what the future might hold to sort of tidy up their predictions made in the past, and at least in this case can get kind of calibration error 0 with good probability. Okay, and this sort of cover-ups is also referred to as backcasting by Foster and Hart. Good. So the main challenge is sort of trying to characterize the power of this sort of cover-up. So to make a start to this, we propose this sort of new game, which is even simpler than this binary this calibration binary prediction setting. And let me describe this new game. So we call this a sidestepping game. And at the beginning of the game, you'll start with k empty cells arranged in a row. And in each round, the adversary is going to choose a cell, one of these k cells. And then the forecaster, us, we get to put an arrow in the cell pointing either to the left or the right. Okay, so here we make a right arrow. And then any arrow that points to the cell that was selected is going to get removed. So in this case, these two arrows pointing to the left are going to disappear. And then the next round, the adversary picks another cell, we put an arrow in that cell, and maybe some of the arrows get removed, and so on. Okay. And so we think of this as a zero-sum game. The adversary is trying to maximize the number of arrows that remain at the end of the game. We are trying to minimize the number of arrows. And let's refer to opt k comma r as the optimum expected number of arrows at the end of a game where we start with k cells and we have r rounds of placing arrows and removing them. Okay, so this is just an example. So we start with the empty, a set of k buckets. They're empty. The adversary points to one of them. We put an arrow in it, say going to the right. The adversary picks another one. We put an arrow in it, say going to the left. Because none of the arrows point to this cell, nothing has been removed. Now the adversary picks another cell, say we pick an arrow going to the right, and this middle arrow that was pointing to this cell now gets removed, and so on. Okay. Any questions about how this sidestepping game is defined?
Is there correspondence that we should see already between like the players in this game and the forecaster and the nature in the previous game? Like it's not even really clear to me who is who.
Yeah, okay, good. So, so I'm going to attempt to describe the intuitive correspondence in this next slide. Okay. And if this isn't clear after this slide, please, we should discuss it. It's not a great slide. Okay, so good. So I'm going to attempt to describe the correspondence between these two games. So think of the original prediction setting, and suppose so suppose we've so far like just predicted a half. Okay. But suppose that the but suppose that, so we've predicted a half so far, and suppose that out of the times we predicted a half, the number of ones is actually greater than half the time we've predicted a half. Okay, so there have been like too many ones. Okay. So this like m sub a half minus 0.5 times n sub a half is greater than 0. Okay, so if we're planning to predict a half at the next time step, then what would the adversary want to do? Well, if we predict a half at the next time step, and the next bit is a 0, then our calibration error is actually going to go down by a half, and we'll be happy as a forecaster. If the next bit is a 1, our calibration error is going to go up by a half, and we'll be unhappy as a forecaster. And in general, if the adversary selects the next bit according to the next bit to be 1 with probability p star, then you expect the calibration error to increase by this p star minus a half. So if up until now, this is a setting we've predicted a half, and of the times we've predicted a half, more than half of those have been a 1, then if we're going to predict a half at the next time step, the adversary would want to choose some value of the next, would want to pick the bias of the next bit to be greater than a half. And this is roughly going to correspond to what's going on in the sidestepping game. So this arrow to the left in the middle cell corresponds to saying, for the value a half, we're hoping, we as the forecaster, as a predictor, we're hoping that the bias of the next bit will lie somewhere to the left of this middle cell, in which case that's going to help us. It's going to erase this arrow here, which corresponds to saying that that's going to decrease our calibration error. Okay. And as the adversary then, if this is the setting, the adversary, we want to pick a cell on the right half so that this arrow remains, so that our large calibration error corresponding to 0.5 doesn't get eroded. Is this okay? So basically the arrows that we're placing correspond to the directionality of where we're hoping correspond to the directionality of whether our predictions have been too big or too small, or whether that there are too many ones or too few ones. And the arrows, and the selection made by the adversary corresponds to sort of naively, would the adversary want to pick a bigger bias or smaller bias, and that might help our various predictions accordingly. Is that at least at a high level clear?
So I guess this makes sense at a high level, but I mean, so if I understand it correctly, the goal for the sidestepping game is really, one person wants to make a lot of arrows survive, right?
The adversary, yeah.
Yeah, the adversary wants to make a lot of arrows survive. So I guess that's slightly different than the goal in the calibration setting, where it's really a quantitative thing about how far you're off on the worst interval, as opposed to like how few intervals, can you make progress in the right direction or something, right?
Yeah, so that's exactly the case. So so here we're sort of saying that in the sidestepping game, like all it takes is one, pointing to a single cell to the left of this arrow, and that arrow disappears. Whereas in the actual calibration setting, we need a bunch of kind of zeros to show up when we predict a half to fix this calibration error. So good, yeah. So that's why we shouldn't really expect an exact correspondence. But we have this following. I guess it's sort of the main lemma, which kind of relates how well you can do in this sidestepping game to the lower bounds for the sidestepping game to lower bounds for the calibration setting. So yeah, let me just read this definition. The specifics aren't really going to be important, but so we say some pair alpha comma beta is admissible if in the sidestepping game, given k squares, where you have k to the alpha rounds of picking arrows, then an expectation you can, the adversary can ensure that there are at least k to the beta arrows remaining, okay, for all k. So, so given this, if you have an admissible alpha beta pair, this gives you a lower bound on the calibration error. That's some function of these alpha and betas. And I guess 2 comments. So in order to get a non-trivial bound on the calibration game, you just need beta to be at least half alpha. If you could show that 1, 1 is admissible, namely given the sidestepping game where you have k entries, you have order k rounds, given that you can prove that the adversary can ensure that there will remain order k arrows at the end, then this would yield a capital T to the 3/5 lower bound in the calibration setting. And we still don't know whether this 1, 1 is admissible or not. So conceivably, working with this sidestepping game, you could get a calibration error lower bound of T to the 3/5. Not quite all the way up to T to the 2/3, which is the known upper bound, but certainly better than what we can do. And in some sense, this could, based on kind of Ankur's comment, like you should expect there to be a bit of a gap because the sidestepping game is kind of so much simpler than the calibration setting. On the other hand, because it's so simple, it's actually, you can actually maybe prove things about it a bit more easily. Yeah. Any, I guess, thoughts or questions?
Sorry, can you just review one more time the definition of admissibility? What are alpha and beta?
Oh yeah, so so we have the sidestepping game where there are k cells and there are R rounds. Namely, there are R rounds of adversary points to a cell. We pick an arrow, and then we might remove some of the other arrows.
And then there have to be k to the beta guys left at the end. That's the
there need to be k to the beta ones at the left at the end. So at least that number left, for all k. Right, so like if you wanted like 1, like alpha equals 1, beta equals a half, you're saying for any k, there's a game with k entries, order k rounds, where the adversary can ensure that square root k arrows remain.
Thanks.
So yeah, I'm not going to say anything about how to prove this theorem. It basically goes back to kind of making this very sort of high-level suggestion of a connection concrete, but and I'm not, I'm not sure. Intuitively, I don't know whether this connection can be strengthened or not, but my guess is probably not. Like, I don't think there's something that, I don't think this sidestepping game could give you like the t to the 2/3 lower bound with a tighter reduction, but I could be wrong. Good. So let me just illustrate a couple of, I'll just sketch the proof of, that you can get some nice admissible things, and then we'll move on. Okay, that's good. So the first fact, for any integer t, given a sidestepping game with 2 to the t minus 1 squares and t rounds, you can ensure that there are at least t arrows remaining, namely, like all of the arrows remain. Okay, if you start with 2 to the t minus 1 squares, the adversary can ensure that none of the arrows ever get removed. How do you do this? It's just kind of the binary search type of thing. So the adversary will pick the middle square. If you put a left arrow in it, then from now on, the adversary will only pick squares in the right side, ensuring that this middle arrow doesn't get erased. Okay, so that should be, does that make sense? So this on its own isn't going to get you anything for the reduction to the calibration setting, but we'll use this in conjunction with something else. So there's also this sort of nice property that if you have some nice construction for the adversary where you start with k entries and r rounds, then this can yield a nice strategy where you have k to the t entries and r to the t rounds, for any exponent t. Okay. And let me just sketch this out. It's kind of, I'll sketch it out in this very concrete case, and it'll be super clean. Good. So suppose given 3 squares and 2 arrows, the adversary can ensure that you always have at least 2 arrows left, which is true. It's such a simple setting that you can argue about that. So I claim that this shows that given 3 to the t squares and 2 to the t rounds, you can ensure that there will be 3 halves to the t arrows at the end. And the picture is kind of as you imagine. You are going to divide the 3 to the t squares into 3 big sets. You're going to play out the game in the middle, and then you're going to look to see, out of this middle game, are more arrows facing the right or the left? And if more arrows are facing the left, then you're going to play out the game in the right side, which is going to erase at most half of the arrows in the middle. Okay, so I wanted to describe this and the previous kind of binary search thing just to give some intuition of how to think about these sidestepping games. And if you just combine these 2 facts, that you can do this binary thing, this kind of binary search together with this, you can start exponentiating good strategies, then you get some horrible expression and you can plot it and you end up with some exponent for calibration that's strictly bigger than 0.5. Okay. So it's not at this point, it's not especially hard proof. It's also not especially interesting, but I think sort of understanding this sidestepping game a bit better actually would be worth doing. And I'm pretty optimistic that one could get quite a bit better lower bounds via the sidestepping game. Okay. Okay, so takeaways from this first part of the talk. I think the biggest takeaway, maybe for me, is that this calibration in this like binary sequential prediction, it's the cleanest, most basic open question in sequential prediction that I know of, and it's still quite open what the right answer is. So I really encourage you all to think about it. Again, the main issue is this notion of cover-ups, and then this new game that we introduced. I think it's an interesting game that's maybe not so hard to analyze, and it feels like something that one should be able to get some tight understanding of. Okay, before I move on to the second part of the talk, any thoughts or questions?
Greg, can I just ask a question? So your definition is a sum over the different P's. I guess I'm more familiar with the one where it's a maximum over a single checking rule, like a window, rather than a sum. And I guess that's the one that's also defined in the Chesabianchi-Lugosi book. So can you comment on that?
Yeah, so this is sort of the definition of calibration, whether you so basically corresponds to, do you want to, if one day I predict 0.51, the next day I predict 0.52, and that sort of thing, do I think of these as completely distinct predictions, or do I bucket them and so on? From the point of view of upper and lower bounds on this calibration error, I don't think there's any difference in these notions, in that you can always kind of discretize your set of predictions without having much of an effect on this. Once you discretize them, then the two definitions sort of become equivalent, and I don't think there's any the nature of the gap between the upper and lower bound doesn't change if you switch to that.
Wait, so is that true? So wait, so the usual upper bound, I guess, that Sasha was talking about is you have an epsilon window over the P's, right? And then you ask, the discrepancy for that one thing. So does the lower bound that you were giving here of the 0.53, does that imply it for some epsilon?
I think so.
Okay. Yeah, I guess I'm confused because so we know that for checking rules with a finite VC dimension, you get square root of t rates, but that's for a maximum over a checking rule, which is you can think of this as a window.
Yeah.
Wait, sorry, is the statement, is the corollary of what Sasha was saying that, for the window-based epsilon thing, root t is the right bound? Is that what you were saying, or did I miss something?
So again, sorry. So what notion? Sorry. So you're doing a maximum over what?
Right. So it's a maximum over a checking rule. The checking rule is essentially something that decides whether to keep this round or not. So, for instance, you for the 0, 1, 0, 1 alternating sequence, you can have a checking rule that just decides to keep the even rounds and so forth.
Mm-hmm.
And this generalizes the window idea.
Yeah.
Because the checking rule can depend on the
Yeah. Okay. So sorry. So that's probably different. Yeah, I suspect that's different.
Yes, there is some difference between the max and the sum that I'm not tracking.
Yeah.
Anyway,
Yeah. So short answer is I'm not sure. I suspect it's different, but maybe we should chat about this at the end if you have a couple of minutes. Does that seem reasonable?
Sounds good. Thanks.
Mm-hmm. Yeah. Okay. Yeah. Yeah. The role of the max seems to be different, and maybe I don't think this lower bound will translate, but yeah, but I'm not positive. Okay, so the next part I wanted to talk about, I guess, a different sequential prediction sort of setting that we're referring to as selective learning, and this is also with Mingda, the same student as the first part. Good. So let me begin with the selective prediction setting, which was a setting I guess first described in this paper of Drucker from, I think, 2013. So nature, or the adversary, is going to choose some length n sequence. It doesn't need to be binary, but let's assume it's bounded. The learner or the predictor is going to observe data points one at a time, observes the values one at a time. And then at some time point t of the learner's choosing, it's going to say, I want to make a prediction about the future. And the form of the prediction will be, I predict that the mean of the next W data points is blah. And at that point, the game ends, the sequence is revealed, and we're just going to evaluate the prediction error, say the squared deviation, sorry, the squared error, squared difference between the prediction and the actual average of those W data points. And again, crucially, the learner is the one who selects when to make the prediction, although it'll turn out that that's not so important. And the learner also selects the window length W over which their prediction corresponds. Okay, and the theorem is that there exist algorithms where the expected squared error is on the order of 1 over log n. And this is optimal to constant factors. So the upper bound was in the paper of Drucker, the lower bound was in this paper of Mingda and I from 2019. And again, this kind of order 1 over log n we found to be fairly surprising and counterintuitive, because the sequence is it's adversarial. It could be zeros and arbitrarily change to ones. And yet this is saying that you can make a sort of accurate prediction of this fairly specific form. And the accuracy of your prediction increases as the sequence grows. And in some sense, the only role of the length of the sequence is that you're forced to make one prediction over this window. So given more opportunity to make your prediction, the accuracy improves. And it's a bit counterintuitive, if the learner isn't allowed to predict, isn't allowed to select when to make the prediction, or if it's allowed to select when to make the prediction but can't change the window length, then you can't hope to do better than a constant error. Okay, and I was going to say, I mean, this sort of result, I guess I view it as like the prediction algorithm is sort of it's sort of empty, and I view this result as more of a Ramsey theoretic type of result that says, given any binary or any bounded sequence of length n, the I guess the moving averages over different length windows cannot behave too strangely. So there must be some consistency at some time scale, given any sequence. So this is sort of a Ramsey theoretic type thing, saying, look, given any length and bounded sequence, there is some notion of local predictability. Okay, so let me describe the kind of selective learning version of this, and then we can go back and maybe discuss intuitions for what's actually going on. So the selective learning version of this is very similar. So nature, or kind of the adversary, is going to choose k length n sequences. And then again, the learner is going to observe data columns one at a time. So the first day, we observe the first value in each of these rows. The next day, we observe the next ones, and so on. And as before, at some time point of the learner's choosing, we're going to say, I'm ready to make my prediction. And we're going to select a window W, and we're going to select one of the rows. And the sort of thing we're going to say is, I think that the row we select, I think that row R is going to have kind of the biggest value, the biggest average over the next W entries. So in this case, I'm selecting, the second row down. This is my window W. And at that point, the game ends, we reveal the whole matrix. And the sort of regret is just, well, what's the average value over these W entries in the row I selected, minus the actual, the maximum row. If I pick the best row and look at the average over those W entries, that's the difference between the thing I pick and the maximum, the best row. That's my regret. And the question is how, algorithmically, what can we do, and how does this sort of scale as k increases? So let me just rephrase this in kind of the language of online learning. The one sentence explanation is, we can think about this as we're trying to output a hypothesis, namely a row, and each of these rows corresponds to the loss of one hypothesis. And in this case, we have capital K different hypotheses in our hypothesis class. And crucially, our notion of regret corresponds to what if we had picked the hypothesis, which in hindsight, for the specific window we selected, would have been optimal. Okay, so let me pull that apart a tiny bit, and then, okay, so yeah, maybe we don't really need to talk about this slide, but the usual kind of online learning setting, you think of some arbitrary data sequence, Z1 to Z sub n. Each of these data points is some labeled point, x sub t, y sub t. Maybe we have some hypothesis class H, some loss function, in this case, some bounded loss function. And at each time step, we're going to select a hypothesis in our class. We observe the outcome and we get some loss. And the kind of usual notion of regret in online learning is, well, we're allowed to kind of pick a new hypothesis at every step. And we're saying, what's our loss compared to, say, the loss of the best hypothesis in hindsight? And in this setting, there's kind of the classic exponential weights algorithm, does quite well, gets this logarithmic dependence on the size of our hypothesis class, and we pay the kind of usual root n. The kind of motivation for thinking about this selective learning problem is, well, what if we kind of only really care about a short interval of time? Like, we don't want to predict something at every time step. We just really want to kind of make our prediction for one, kind of short, discrete time interval. And for that, the benchmark really should be, well, the best hypothesis for the little interval that we're trying to, make our prediction for, not the best hypothesis over some enormous time horizon. And then also, there's been a lot of recent work on, well, what if you don't want to be switching hypotheses at every time step? What if you, need to pick a hypothesis and stick to it? And this has been captured by various different works recently, where you have switching costs, or bounded number of switches and so on. And then also, I guess we have this selective component where we're going to commit to a single hypothesis over some window that the learner is allowed to select. Okay, so we could phrase this as the selective learning. We still have this kind of arbitrary data sequence, some hypothesis class H, some bounded loss function. And at some time t of our choosing, we pick some window of length w, we pick a hypothesis h hat, and then we're going to incur this excess risk, namely the loss we get over these next w time steps minus the loss, count the best loss of in our hypothesis class over these same w time steps. Okay. Any questions, I guess, about the setting, or complaints about the motivation? That's also a fair game. So if you really care about learning, there's this kind of learning interpretation. You can also think about it as just this Ramsey theoretic type of question where, given a single sequence, there is this level of predictability. That's what this theorem says. Even worst case sequences are predictable at some time scale. And this selective learning question is sort of saying, look, suppose you have this matrix, you reveal columns one at a time. To what extent is there still this sort of notion of predictability? So you can think of it as kind of the Ramsey theoretic type thing, or more of a online learning type of problem. Good. Okay, good. So right. So if you have independent data, then if you're trying to predict the mean, well, you get the usual 1/√n. If you're trying to do this online learning with respect to some hypothesis class H, then you can get this root log size of your hypothesis class over √n. As I mentioned in this just selective prediction setting, you get this 1/log n, the square root, 1/log n if you want the expected squared error. And if you just kind of push these techniques through to the selective learning setting, you get this root size of hypothesis class factor. And basically the question is, should you be able to hope for something that's maybe polylogarithmic in the size of your hypothesis class, or maybe even something even better. Okay, so any guesses as to what kind of the right answer is for the selective learning question? Like, what should the dependence on the hypothesis class be? A bad guess is better than no guess.
Okay, we have a guess of inverse Ackermann in the chat from the watch party.
Oh, okay. Nice. That's actually not such a bad guess. Yeah. So the right answer is actually this log size of your hypothesis class, over log n, and I guess from this kind of Ramsey theoretic point of view, I was very surprised by this. So it kind of means that if the adversary is trying to fill up this matrix of rows, there's nothing too tricky that it can do. In that, if it's trying to make these, you're trying to guess which is the best row for your little window, and there isn't really any way of making it all that hard. Like, as the number of rows increase, it's kind of very hard to start hiding really good rows without you being able to find them. And this is sort of, I don't know, I found this very surprising. Yeah, so, good. And then we also have this kind of interesting, and that log, it's tight. And we also show this kind of surprising thing that if your predictor is going to, picks its window length W and makes, predicts which row just as a function of the previous W columns, then you basically lose a log factor, or not a log factor. You lose like you lose a log. You use like an exponential. Good. So let me. Maybe I'll go for 3 more minutes. Okay.
Sounds good.
So let me sort of say a little bit about what goes into this. Okay, so good. Okay, so the sort of algorithm which gets a linear dependence on the size of your hypothesis class is the following. Pick a window, W, uniformly from the set 1, 2, 4, 8, 16, blah, blah, blah. Pick the time at which we're going to make our prediction uniformly between 1 and n, maybe making sure that, or uniformly between 1 and say n minus W. And then just return the hypothesis or the row that has the largest average value over this kind of training set, over the previous W entries of our window. Okay, so like at time t, we make our prediction. We're going to do it to be like the empirical risk minimizer over the previous W time steps. Good. And okay, and this gets you this kind of polynomial linear dependence on H or square root. Okay, in order to go from that square root to the logarithm, all you need to do is do kind of a soft ERM. So you just need to pick your hypothesis according to sort of maybe a slightly cleverly weighted, the right kind of exponential distribution. And the proof is kind of, the proof is pretty intuitive. So think of P sub x to be this distribution, this exponentially weighted distribution over your different hypotheses based on the performance on the training set, namely the previous W time steps. P sub y is going to be this corresponding distribution over the actual, the values in the next W time steps. Of course, we don't see, we don't know P sub y until after the game's ended. But the claim is, if we saw the future, if we knew kind of y and P sub y, then if we predicted according to this, P sub y, then as long as alpha, our scaling is large, then we'd have small sort of excess risk because, well, we're picking from a distribution that puts lots of mass on the good hypotheses. And then there's a bit of an argument to show that with respect to the randomness in our choice of the window and when we make our prediction t, actually this kind of exponentially weighted distribution corresponding to our training set is actually close to the exponentially weighted thing of the actual test set, provided alpha is kind of small. If alpha is small, then this correspondence is very good. And basically, we'll end up picking alpha to balance. We want alpha to be large so that the the risk of P sub y is small. We want alpha to be small so that the training and test set sort of an expectation end up being similar. We'll pick alpha to kind of balance these. One more minute. Okay, and then the kind of algorithm that yields the final log is actually we end up picking a longer window. So we're gonna make our the window length we're picking is little w, and then we choose that from the same distribution that has equal mass on 1, 2, 4, 8, 16, 32, and so on. Then we're going to pick this slightly longer window, capital W, and we're going to do this kind of exponentially weighted different hypotheses according to this longer window. And this is what kind of buys us this extra, let's just put the extra log in front. And just I'll just make the picture. The sort of intuitive reason for this is the algorithm ends up being basically equivalent to running exponential weights on these kind of log n fictitious instances of the kind of ordinary online learning problem. So these are the, okay. Maybe let me end here. So it's sort of okay. So just some open questions. So yeah. So it's super cool that the people in the chat were actually optimistic that you could get some like really tiny dependence on the size of the hypothesis class. I was very surprised that you could get this log, in part because I spent lots of time trying to show that a polynomial dependence on the size of the hypothesis was actually necessary. So I guess there are a bunch of open questions. One sort of higher level one is sort of bridging this gap between independent data versus worst case data. So I don't know of any great models where you have the sequential setting that's basically IID, but with some limited amount of corruption. And I'm not really sure to what extent you can hope to recover, kind of 1 over n's versus 1 over, log n's. There's a computational question that, the current algorithm that we're proposing, you can make it computationally efficient if you can kind of sample, if you can efficiently sample from this hypothesis class, although there are lots of hypothesis classes for which you cannot efficiently sample. And it might be possible to have algorithms that are not kind of sampling based. And then even higher level, these sorts of kind of strong guarantees in settings where the data is kind of worst case, yet despite that, you're still able to make these, you're still able to kind of learn, although I put learn in quotes because in some sense, the future is not like the past. You're not really learning, but you're making good predictions. So, I feel like there's a whole world of other sorts of models and results in this sort of high level view. Okay, so let me end there.
Thanks, Greg.